Hello, everybody. Welcome to week 2 of Zoom. We're going to continue our discussion of hybridization and bonding today. And we left off talking about sp3 hybridization the other day. And let's go take a step back so we can move forward. Over here, we have hybrid orbitals, which come from atomic orbitals. And they're used for two things. They're used to make sigma bonds, or they're used to put lone pairs in. What do we use p orbitals for? Those will be used to make pi bonds. Here's a translation of that sentence, these two sentences. If you need to determine the hybridization of an atom, you're going to add the following two numbers: the number of sigma bonds that you see and the number of lone pairs. If you add those numbers up and you get 4, then the name of the hybrid is sp3, SPPP. If you count sigmas and lone pairs and you get 3, then the name of the hybrid is sp2, SPP. If you count sigma bonds and lone pairs and get 2, then the name of the hybrid is sp, you get sp. For example, we're over here where I see only one bond between C and H right here. When there's only one bond between two atoms, that is called a sigma bond. I have a sigma there, a sigma there, a sigma here, and a sigma here. For sigma, sp3. That's the same for this carbon here and this carbon here. This carbon over here has 3 sigmas. That's 3 fingers. Sigma, 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 and a lone pair. That's 4 things. Lone pair is one, that's one lone pair. I didn't say electrons in lone pairs, I said lone pairs. So once again, sigma, 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 and a lone pair. And I even mentioned this oxygen. I don't know if I mentioned the chlorine. The chlorine is also sp3, 1 sigma, 3 lone pairs. That's 4 things. Okay, let's focus on these carbons. The angle when you're sp3 hybridized is 109.5. sp3 is going to give you 109.5. Now, if all 4 of those positions are atoms, then the geometry is tetrahedral. Tetrahedral, tetrahedral, tetrahedral. Now, in this one, where only 3 of the positions are atoms and 1 is a lone pair, the geometry is not called tetrahedral, even though it's the tetrahedral angle. These are 109.5, and even the angle to the lone pair is close to 109.5. But when we do the experiment called X-ray crystallography that gives us the actual structure of these species, it's a pyramid, because the X-ray doesn't bounce off of a lone pair. It goes straight through. But the lone pair does cause these H's to be pushed downwards. Otherwise, it would be trigonal planar, which we'll see when we do sp2. So the lone pairs do have an influence on the H's and cause a pyramidal geometry. Now, in terms of bonding, it says here hybrid orbitals are used to make sigma bonds or to put lone pairs in. Well, what I've done over here is I've come up with a molecule, CH4. How do you know it's sp3? Well, it's got 4 sigma bonds. It's this molecule right here. Here are the hybrids off of carbon. They're overlapping the only orbital that hydrogen has available for bonding, which is an s orbital. Hydrogen is in the first row of the periodic table. There's only s orbitals available to both atoms in the first row. You cannot hybridize one thing. Hybridization is a mixing of more than one thing. So whenever hydrogen makes a bond, the orbital it provides to make the bond is always the s orbital. So the s orbital on this hydrogen is going to overlap with this hybrid orbital that's sticking straight up. It's going to make what's called a new orbital called a bonding orbital, which is a molecular orbital. And the name of it is named after the two pieces that were used to make it. Carbon provided an sp3 hybrid. Hydrogen provided an s orbital. After they overlap, it is a new entity entirely. The new entity's name is sigma sp3-s. It is a sigma molecular orbital caused by the overlap of an sp3 on carbon with an s on hydrogen. And every orbital, every bond in this molecule is now a molecular orbital with the same name. There are 4 of them. Okay, so that is the story for sp3. For sp2, we count the same as we counted before. So for example, this carbon here has a sigma bond here, a sigma bond here, and the first of these 2 bonds is a sigma, the second is not. The second is that's a terrible looking sigma, but those are all, okay, I'm not happy. My pen doesn't like me pushing too hard. That's one thing I've learned. I still couldn't get it to be the same. 3 sigmas, no lone pairs. You're holding up 3 fingers in the air, and your conclusion with 3 fingers in the air is always the same. It is sp2 hybridization. The angle for every sp2 hybrid is 120. It should make sense that the angle is bigger. We're getting 3 things apart from each other down here and here and here. Up here, we're getting 4 things apart from each other. You can't get 4 things as far apart from each other as 3, so the angles are bigger for 3 than 4. You only have 3 angles to memorize in this course, which is nice. The sp3 angle, 109.5, the sp2 angle, 120. Both of these carbons are sp2 for the same reason, sigma, 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 that's 3, and the top carbon, sigma, sigma, sigma. All 6 carbons in benzene are sp2 for the same reason. All of them are trigonoplanar in geometry. Now, if we have this species here, it has a sigma over here. Oh, that's a highlighter. We have a sigma over here and a sigma here and an LP here. Count them up, that's 3 things. That's why it's in this sp2 box. But when you're describing the geometry, even though the angle still 120, because that's the sp2 angle for this course, we don't describe the lone pair because we don't see it. We describe this geometry that we see here, just this bend. And it's got a good name for something that's just a bend. It's called bent. Okay. Let's look at the bonding of this second example. We have ethylene. I have it again over here. We've already determined that both carbons are sp2, so I have the hybrids showing here, sp2, sp2, sp2 hybrids. When it bonds to H, it's overlapping with the S on the H. The name of the orbital is a sigma between an sp2 on carbon and an S on H. So that's the name of these 4 bonds. The sigma bond between the 2 carbons, which is the first bond between the two carbons is a sigma again, and it's an sp2 on the carbon on the left and an sp2 on the carbon on the right, and the name is right there. The only orbital we have yet to describe is the I was looking at the clock here and I got sidetracked. Yeah, we haven't described the pi bond, have we? The pi bond is right here. I don't see it in here. These are all sigmas. I did the sigma picture here. I had to rotate the molecule to show the pi bond, and I replaced all of the bonds that were like fully drawn out here. And by the way, you will never have to fully draw a bond with a hybrid orbital and a s orbital or two hybrids. From now on, we're going to draw lines, sometimes wedges and dashes. What I had to do, and there's a reason for it, I rotated the molecule 90 degrees because to show the pi bond, I need to use the p orbital that's as far apart from these as possible. And please remember the geometry here is trigonal planar. So everything here is in the plane of the page. So if I picked a py orbital, which is straight up and down, it would only have a 30-degree angle to this one, which is at 120 to this. The p orbital here is 90. That's not a good p orbital to use. You already used that p orbital. You know what you used it for? To make the hybrids. The only p orbital you didn't use is the one that's as far apart from these sigma bonds as possible, and that's the pz. It's sticking out of the page at 90 degrees to this orbital, and the back half of it is behind the page at 90 degrees to all these orbitals. That's the best you can do with a pi bond, have it 90 degrees to the sigma bonds. So I rotated the molecule 90 degrees. So now the plane of the page includes these 6 atoms right here. And the carbons are in the plane. The plane is coming at you like this instead of my original, which was like this. I don't know, my original plane
Professor?
was like this. What's happening? I'm moving my hands a
Sorry to
lot.
interrupt.
Sorry, go ahead.
I was a little confused about like the naming behind the pi, py's, and px's and z's. So is that just based on what axis it is, or is there anything else we should know?
Naming is your discretion. We have to, I haven't got to the pi bond yet, but hopefully I answer your question. I think I know where you're coming from. Remember, a molecule doesn't know which way you're looking at it. So I could rename this pi pz right now, and that just means I'm looking at it with my eyeball up here instead of my eyeball looking head on the way it's looking on the page here.
Right, okay.
So, but the thing is, to get a pi bond, you need the p orbitals to touch each other. If there's not touching, they clearly can't be overlapping. So you will not have any overlap between a py and a px. They're in the wrong plane. You'll never have an overlap between a pz and a px. They must have the same name because that's the only time they could be touching each other. So I just rotated 90 to make it so you could visually see the p orbital and the sigmas at the same time. If I tried to draw the pi bond here, you wouldn't see it. It's sticking straight out of this carbon. And how do I draw that on a piece of paper that's flat? I can't.
Right,
so I just rotated, and I'm glad I helped you there.
Okay, thanks.
Okay, so I just redrew the sigma bonds like bonds instead of having them like these. And then there's the p orbital that you didn't use when you hybridized an s with 2 p's. Remember, there's always 3 p's to account for. And the third one is the one you haven't used yet. We're about to use it right now. I'm taking the unhybridized p orbital on this carbon, and it's touching the unhybridized p orbital on this carbon. After they overlap, it's now a new orbital. It's no longer called a p orbital and a p orbital. They are now overlapping, making a molecular orbital. And the name of it is a pi molecular orbital. And you have to tell me that you know the 2 p orbitals used to make it are identical on each atom. So these must always match, and it is totally your discretion to make them have the same letters. You could use px, px, you could use pz, pz, or py, py. And there we have the whole story of bonding for sp2. And we're going to move on over here for SP. Top of the page here. I keep repeating these for a good reason. It's the foundation of hybridization. It's what are hybrids used for. So we're going to look at this carbon here. I see a sigma on the left. And only one of those three bonds on the right is a sigma. That's two sigmas. You put up your two fingers and you've got SP is the name of the hybrid. And it also tells you how many hybrids there are. 1, 2. And there you have it for SP. Looking for my highlighter here. SP, the magic angle is 180. And we call that a linear geometry between the H and the C, and the C, H goes to C straight through a line there. It's like this guy's in the middle. And the carbon in the middle here is also linear. It has two sigmas. It's 180. And we don't do geometry when it's just two atoms. Now, A bonded to B is the name of the geometry. There's no way to describe that. They're next to each other. How's that? So in terms of the bonding, I'm going to skip straight past the sigmas. I'm going to look at their names, and I hope we're not surprised that it has a slightly different name. The carbon is SP, as we determined over here. SP and SP with the two sigmas. The hydrogen is always S, so those are SP-S, both of them. And the carbon to carbon sigma bond in the middle, which I just drew as a stick, is S sigma SP-SP. The two hybrids are overlapping. Now, clearly we haven't accounted for two of the bonds when we did the sigmas. These are all the names of the sigmas, sigma there and sigma there. There's a pi here and a different pi here. They have to have different names because different orbitals are overlapping. So this one looks like the one on the previous page. There's the py overlapping the py on the top and on the bottom. Now PZ, a little tricky to draw, but I have it sticking out of the page out here, and I have it going in behind here, and this one's invisible almost totally because it's hidden by these, but it looks just like this, but it's behind those two. And that's a new pi bond called PZ. Pi, PZ. Pizza. It's getting close to dinner. All right. So we should be able to do the description of any bond in a molecule. So on your test, you're going to be given, actually, you'll be given a version of this that's typed out, and then you're going to have to create the Lewis structure from the typed out version. We're still not quite ready for all these new functional groups, although we hinted at carboxylic acids the other day. On Monday, we're going to learn this is an ether. Or, I don't know, today? We'll see how far we get. And we're going to learn this is an amine. Anyway, I copied the molecule twice so you can see where the original question started. And we can do the hybridizations maybe on the left and then name all the bonds on the right. So let's just do hybridizations. We're going to count sigmas and lone pairs for every atom, and I'll put the number of sigma bonds on top and lone pairs on the bottom. So carbon here has 3 sigmas, 0 lone pairs, and it's trigonal planar. Can I just go TP for all trigonal planar for the rest of this discussion? And we have the same scenario for this one. TP, 3 sigmas, no lone pairs, and I believe this one also TP. And we didn't put the hybridization there. We put the geometry. We got more information than I was ready for here. We put the geometry. But you can't do the geometry unless you did the hybridization. It's SP2. Okay, how about the nitrogen? It's got Sigma, sigma, sigma. 1, 2, 3, and a lone pair. So it's pyramidal because it's sp3 with one lone pair. sp3. Having trouble with my p's. All right. These carbons are both sp and linear. sp and linear sp. And we have carbons that have 4 sigmas, 0 lone pairs. My nitrogen had 3 sigmas and 1 lone pair. And 4 sigmas, 0 lone pairs, that's called tetrahedral. And it's tetrahedral because it's sp3 and it has no lone pairs. And oops, I didn't draw all the bonds to my CH3, but I know those are all 3 sigma bonds. So we have tetrahedral. I need a short form for tetrahedral. Tet, sp3, oxygen, 2 sigma, 2 LP, sp3, bent. I don't know, do we have an sp3 bent before now? I know we had an sp2 bent, but we're just describing the bend here. That's bent. And we don't describe geometries of atoms on the end like H's or this O. And I think we're ready to do the important part. And the important part over here, did all the hard work over there on the left, but we're going to get the points on the right. Over here, we're going to do name each bond, and B, determine the geometry around each central atom. And I need both. I need both the angle and name. So actually, we use this as an exercise opportunity for you. If you've copied that molecule down, which I know some of you haven't, which is fine, take in the video, then copy and write notes later is a perfectly good strategy. But if you haven't, copy it down now, because we're going to take our 5-minute break. And when we're done, I want you to tell me what kind of sigma bond that is, and tell me this one's the same, and what sigma bond this is, and then what pi bond that is. All of those things. Every bond in this molecule is going to have a label when we get back. So I'm going to move that down and end this segment. I have a nice short intro segment here. We got a question first?
Yeah. Before we enter, we answered the names of the angles on the other side where we said pyramidal, bent, tetrahedral?
Yeah.
So that part is technically done, right?
We're going to do that in part B. Yeah, we're going to say this one is trigonal planar 120.
And then if it's tetrahedral 109.5, and then
yes,
184.
Sir. Yeah.
All right, yeah.
And when I come back, I'm going to have this CH3 redrawn with all 3 bonds showing. Okay?
Okay. Give me 1 second. Let me copy the thing real quick.
All right. Don't want to have dead space on our video though, so go ahead and do your best shot. You can do a screenshot. You know how to do that?
On a laptop, I think snipping tool, right?
Snipping tool or print screen, and then paste it into something like Paint. Print screen is one of the buttons on your keyboard. Top of the keyboard near the right side. And that puts it in memory that you can paste into Word or Paint.
Okay, got it.
All right? All right, we shall see you on the other side. And we're going